with the support from RUSA 2.0. It is my pleasure to welcome today's speaker, Professor Sir Michael Berry, to this forum. I don't need to introduce Professor Sir Michael Berry to the physics audience. Professor Sir Michael Berry is a well-known person among not only international community, but also Indian physics community. He is a regular visitor to India and written several papers with Indian physics. In fact, he had also visited Department of Nonlinear Dynamics, Bharathidasan University, and interacted with us. Since more than half of the participants present online today are postgraduate students, I would like to read out his discoveries in physics in a brief manner so that the young students can get motivated. He is well known for Berry space, a phenomenon observed in quantum mechanics, optics, and also some other areas in physics. He is also known for Berry conduction and curvature. From the literature, one can also see he is known further for Berry-Robbins problem, Berry-Debye conjecture, Berry conjecture, quantum corpets, and quantum chaos. From this, we can understand his original contributions to semi-classical physics and optics. He has written around 400 research papers in this area. For his discoveries, he has received several awards and honors. To name a few, I read chronologically: Maxwell Medal and Prize, Fellow of Royal Society, Royal Medal, Dirac Medal, Naylor Prize and Lectureship, Knight Bachelor Award, Wolf Prize, Onsager Medal, Polya Prize, and Lawrence Medal. He had also received several honorary doctorates from several universities around the world, including one from University of Hyderabad, India. Due to time restriction, I didn't read all the honors which he had received for his contributions to physics. We are really fortunate to have him today. I insist the students to visit homepage and learn more about his works and his commitment to physics. With this short introduction, now I invite Professor Sir Michael Berry to deliver his lecture. Over to you, sir.
Good. Well, thank you for that introduction. I must begin with an apology. I only realized yesterday, after preparing this talk, that this series of talks, of which this is one, is on nonlinear dynamics. Now, this was clearly stated in the invitation from you, but somehow I didn't pay attention to it. And I'm not speaking about nonlinear dynamics. It's a long time since I worked on that subject. However, I hope that this talk will be interesting to any mathematical scientist, as I understand most of you are. So here goes. I'm speaking about physics and mathematics. Now, they are intimately connected, and they always have been. Now, sometimes for educational purposes or whatever, it's convenient to treat physics and mathematics as separate subjects. But in our everyday scientific practice, it can be sometimes very difficult to tell them apart. And I'm deliberately going to confuse them in this in this talk. I want to quote a beautiful description of this connection by Peter Atkins. He's a writer of chemistry textbooks. Determining where mathematics ends and science begins is as difficult and as pointless as mapping the edge of the morning mist. And I spend my life wandering in and out of that mist, as most mathematical scientists do, although we don't always really appreciate this explicitly. Now, nowhere are the intimate connections between physics and mathematics more immediate than in optics. With our own eyes, also our brains, which I'll return to at the end, we can see almost directly through physical phenomena to mathematical phenomena. And I'm going to show you some mathematical phenomena and their counterparts in light. Turning mathematics into light, indeed, as my title suggests, or maybe it's the other way around. So let me start with some mathematics you probably all know 1 + 1 = 2. Nothing could be simpler. And indeed, it applies if you have 2 torches or 2 flashlights, the intensities add. But this is actually applied mathematics. For pure light, intensities do not add, and 1 + 1 is not equal to 2. Now, you should not be surprised by this, because when you think of a mathematical expression as applied mathematics, it doesn't always apply. For example, if 2 people come together and produce a child, 1 + 1 = 3. If on the windshield of your car, on your window, 2 water droplets, 2 raindrops coalesce, 1 + 1 = 1. You have to be careful when you apply mathematics. Now, in the case of light, it's waves that add, and they can be in or out of phase. And if you have 2 waves, the difference of phase can cause interference. You all know this, and here's the intensity of the 2 as a function of the phase difference. And you see it varies between 0 and 4, and in particular it can be 0, and I have to come back to this much later. So this poses a question. If light really does have this behavior, why are 2 torches twice as bright as 1? Well, because torchlight is messy light, and the phase is varying rapidly and randomly. Now, so the intensity is something like this, much too fast, these variations, for us to perceive them. So we perceive the average, and the intensity averaged over messiness is equal to 2. This comes to the average of cos squared as a half. Now, this means that 1 + 1 = 2 is recovered now, and it's quite a subtle thing. It's not a straightforward matter. Nowadays, we call this decoherence. The idea goes back actually to Thomas Young in 1801 or 2. He wondered why you don't see interference, which he was emphasizing is evidence that light is a wave, why you don't see interference all the time. And he realized in a qualitative way what I've just described. It's what we now call decoherence. It's central to the, it's one central aspect of the emergence of the classical world from the quantum world. That's a separate matter. I'm not speaking about that today. Okay, here is interference near a line of focused light. A line of focus, a caustic. I'm going to use this word repeatedly, and I'll explain it in detail as we proceed. So here's the phase difference. And where would one see such a thing? Well, one sees it in rainbows. And here you can see these interference fringes. They're supernumerary bows. Supernumerary was surplus to requirements, unwanted. And that's because in Newton's picture of light as particles moving in rays, there was no interference. And when people began to observe these fringes shortly after Newton died, they were puzzled by them. And Thomas Young realized that it's interference that one is seeing. So here's another example. Here you see it, just one fringe. You don't always see them because decoherence. If the raindrops are very different sizes, the fringes are blurred out. But if the raindrops are almost all the same size, and that depends on meteorology, then then you do see them. And here it is. And why I'm showing you this picture is that it's an iconic picture because this is the house where Isaac Newton was born. So this rainbow with its supernumerary fringe, which he could not understand, you can think of it as being ironic. It's almost mocking him. Good. Well, what is actually happening here? Well, here's a raindrop, and here's the sunlight coming in, and the emergent rays are what you see. Now, it turns out, when you do the calculation, that there are, in every direction of emergence, there are 2 rays. And of course, they have a phase difference. And so as you change your view, as you look in different directions, this phase difference varies. And so you have these interference fringes. So that's what's actually interfering in the rainbow. If you plot the deflection as a function of impact parameter, place where the sun, labeling the sun ray that comes from the sun, it's a curve with a minimum. So here are the two rays, this one and this one, that come out in the same direction. Now, this is a piece of mathematics. It's a 2-to-1 map. So a rainbow, you're seeing these fringes, is a 2-to-1 map. And as you look closer and closer to the connection between the two, that's a singularity of the map. The two come together, and that's the bright rainbow direction that you see. So rainbow is the bright arc of a rainbow is a singularity of a 2-to-1 map. Good. Well, here is water sparkling on the surface of actually Bristol Docks, where I live. There are places where the wavy water is sloped so as to reflect sunlight directly into your eyes. It's a many-to-one map. You're actually seeing the images of the map from the sun to the eye via the water at any given instant. Now, this map has singularities. These points come together over time because the water is waving and these points move around, and they come together in pairs, or they appear in pairs. Now, these are singularities of the many-to-one map, and what's happening is you have to think of the light, reflected light, in the space above the water. You only see those rays that enter your eye, but in the whole space there are reflected rays, and they form caustic surfaces. And when one of those caustic surfaces passes your eye, then that's one of these coalescence events. They're called twinkles. Their rapid appearance, rapid succession is responsible for the sparkling appearance of the water. So here you see some wavy water, and here are the reflected rays. And depending on where your eye is in relation to these caustics, you see 1 image, 3 images, 5, or whatever. So that's the picture. Underlying the sparkling of water is this these repeated singularities of a many-to-one map. Now, the mathematics that describes all of this is catastrophe theory. It's a branch of geometry. I won't explain the origin of the name. It comes from a different application. It's a branch of mathematics invented, discovered in the last decades of the century just gone by. Now, that's several hundred years after the laws of geometrical optics were established. You know, reflection, equal angles, Snell's law, and so on. So it took all that time for the mathematics to develop, which enabled many phenomena, as I'll describe as we proceed, to be understood that couldn't be understood properly before. Now, what this mathematics does, it describes caustics that are stable under perturbation. That's natural focusing. I will give you an example of it in a little while. Now, so caustics in optics are the physical embodiment of mathematical catastrophes. They're focal lines or surfaces of families of rays. So here's a picture again. This is from a wavy lens or mirror, reflected or refracted. And here you see the rays, and here you see the caustics, which is the envelope of the family of rays. It's very important that these phenomena involving focusing are holistic properties. You know, no single ray can come to focus. You have to have a family of them, and in optics you always do. Now, the classification depends on codimension. That's the number of parameters you need to explore to find something. So the first of them is called the fold catastrophe, and that's because indeed it looks a little bit like a projected folded surface. This has codimension 1. You need to explore only one parameter in order to encounter this focal line in 2 dimensions. It's a surface in 3 dimensions. In 1 dimension, it's just a point. So that's codimension 1. And next one is the Cusp catastrophe, codimension 2. And here you see it. It's a point in 2 dimensions, or it's a line in space. You'll see examples soon. Many examples. You've all seen the cusp in the coffee cup, reflection from the inner surface of the cup of some light source, light in the room or the sun outside, projected onto the surface of the milky coffee and diffusely reflected. I'm friendly with an artist who lives near me, and she creates these structures which she calls light catchers, and you see beautiful cusp in the sunlight. If you wear glasses and you walk outside when it's raining, raindrops fall on your glasses, water droplet lenses on the lenses, and if you look through at a distant streetlight, you'll see its image distorted into a many-cusped figure. These cusps form naturally. Now, in 3 dimensions, we have a point in space. I won't go further in this classification. 3 dimensions, points where you see 2 cusp edges meet, codimension 2, and these themselves are places where 2 surfaces meet, which are codimension 1. So the higher catastrophes contain the lower ones. There are actually 3 singularities with codimension 3. And here's one of them, and name is not significant today. It's a place where 3 cusp edges meet, and the hyperbolic umbilic is a singular point is where a smooth outer surface meets a cusped inner surface. Now, it was a surprise that these shapes that I've described are the only stable singularities in 1, 2, and 3 dimensions. We'll make use of that just now. No, in a moment, excuse me. If you take a piece of bathroom window glass and shine a laser through it onto a screen, you will see beautiful caustic shapes. Now, the kind of bathroom window glass I'm thinking of is one that has random, smooth irregularities on a scale of about a millimeter or 2, the size of the laser beam. And what you see depends on where you put the screen. Here, lots of little 3 elliptic umbilic triangles and lots of smooth fold curves. And here, if you look into the far field, you see structures of this type. They form naturally. Now, I want to explain this notion of stability with a beautiful astronomical phenomenon observed in 1976, where a star was occulted by the planet Mars. Mars moved in front of this star and blotted out its light. That's a rare event for a star that's not particularly faint, because with faint stars, it happens all the time. But this is a relatively bright star. So this means that if you're suitably positioned on the Earth's surface to see this phenomenon, the light from the star will disappear and reappear a few minutes later. And an airborne observatory was flown into the path of this phenomenon to see this switching off and switching on. But Mars has an atmosphere which bends the light into the shadow, and here it is, so that when you're on the Earth, if you're positioned in the right place, in the middle of this event, the light will switch off and then later switch on, but in the middle there should be a flash as this focal line that crosses your camera. Now, the actual focusing from Mars, the sphere of Mars, by the atmosphere, is a spun cusp, which you don't see, it's too far away, but here's the focal line. Well, they looked, and indeed, here's 6 minutes, or so, they saw this central flash. The light switches off, and then the line caustic comes as predicted. But there is something unstable about this phenomenon. because this focal line does not appear anywhere in the catalogue of the classification I've shown you. It's therefore unstable. And what will break the symmetry? The fact that Mars is not a sphere. It's, to a next approximation, ellipsoidal, and that atmosphere is therefore not a spherical lens, but a distorted lens, and that's enough to break the symmetry. It does this, you can calculate it. Instead of the focal line, you get this 4 hyperbolic umbilics, so you would see in a plane a 4-cusped asteroid. So this suggested, or indeed predicted, that this central flash actually would have a fine structure. And here's what they predicted. The path of the telescope on the aircraft through this cusped caustic is as I've shown it. So you should see inside the central flash, we're speaking of seconds now, if you zoom in, you should see 2 fold singularities. So the prediction was that in seconds, this is a magnification of the 6 minutes of the whole event, you should see these 2 singularities. And when they did magnify, they saw this. And that is a really beautiful example of a stable singularity resulting from a symmetry breaking perturbation. It's a deep and beautiful thing. Now I introduce my wife. Some of you know her. You've never seen her like this, and that's because she's being reflected in a curved mirror, a mirror which itself has a point of inflection, a large sheet of illuminized plastic, which is folded over, so its curvature changes sign. She is fixed and I'm moving the camera. How does one understand images of this sort? The simplest way is to think of a picture, her, as a collection of curves. Well, for example, contours of intensity. Now, each point on a curve emits a family of rays in all directions, right? So the curve corresponds to a family of families of rays. And its image is also a curve. It's a distorted and often topologically disrupted image of the object curve. Now, you've all seen this on water. For example, here's a boat, and what you don't see, it has a mast. The reflection of the mast is distorted. It's also topologically disrupted, and there's a theorem about where and how this disruption occurs. Of course, it's to do with caustics. And here's another such picture. This is the image of a single curve, but you see it's complicated. Now, a picture, a collection of curves, is therefore a family of families of families of rays. And as the viewing point changes, images of different curves, different parts of the picture, change topology at different times. And you have to understand that in order to understand the images that you see. Now, people who work on gravitational lensing of, for example, dark matter clusters as distorting the image of a distant, for example, a distant galaxy, know how to calculate these images. But what is not done there, and I've done it recently myself, is to understand how the images are organized by different catastrophes. And this is different from mirrors which are curved in one dimension or mirrors that are curved in 2. I just want to show you some pictures. I don't want to go into details. It's a long story. So here's the cusp. It's me. It turns out that I've chosen just this image such that the rays from one of my eyes in the middle here focus onto a cusp which passes through the camera that I'm using to record the picture of myself. Here's the elliptic umbilic picture, and here's another one, a different stage of the unfolding, and here's the hyperbolic umbilic. Again. So these weird and wonderful distortions can all be understood using this singularity theory. It's optics and mathematics intimately connected. Now, you will have noticed, indeed I showed you near the beginning, waves decorating these caustics. I showed you this picture. Well, it turns out that each of the types of caustic, each of the mathematical catastrophes, is decorated by its own characteristic wave pattern. And I want to tell you about those. So this is the fold, and it's decorated by an integral discovered by Airy in 1838. Here's the intensity is the square. Call it the squarey function, if you like. You see this everywhere. For example, in water waves, Kelvin's ship waves. You're familiar with this V shape decorated by waves. Well, here it is. This V is a caustic of the rays of the water waves. You can describe, it depends on the dispersion relation for gravity waves on water. If the water is deep relative to the ship, this always has the same angle. Its half angle is arc sine 1/3. And across here is the Airy function. It really is ubiquitous. That's what stable means. Here's focusing in space-time, a tidal bore near where I live in Bristol. There is one on the Hooghly, the barn near Calcutta. There are a few of them around the world. They come where the advancing tide catches up with itself, and instead of coming in gradually, comes in as a interesting waveform, which when you calculate it is actually the integral of this Airy function. And another example, often confused with this, but distinct from it, is a tsunami. These are the most destructive of all natural phenomena, as you well know in India. There have been some very destructive recent tsunamis. Well, these are essentially Airy functions that travel across the surface of the ocean. Good. Now, let's go to the cusp. I've shown you the fold. Here's a wave decorating a cusp. And part of the pattern are pairs of perfectly black points, zeros of intensity. I want to discuss these. You don't see them very clearly here, but they are there. So I want to discuss zero. I said that nothing is simpler than 1 + 1 = 2. Well, let's talk about nothing. Much ado about nothing. Complete destructive interference. If I compute this cusp diffraction catastrophe, here's the intensity color-coded, but also the phase varies from place to place. So, and zeros, these zeros are singularities of phase, because if the intensity is 0, you can't tell what the phase is. And indeed, if you plot the phase color-coded around the color circle, you see that at each 0 here, you have a place where all the colors, all the phases run together. So the phase is undefined at such places. Now, these zeros are much more general than simply associated with the waves that decorate caustics. So, for example, if you see random waves traveling in many directions, here's 2 wavelengths square of, I think it's 10 plane waves going in different directions. You see some zeros, but if you plot the phase, then you see that each 0 corresponds to a phase singularity. This is optics on the finest scale. It describes many things: laser speckle, section of black body radiation, electron waves in a chaotic quantum dot. It's wave physics on the finest scale. And in 3 dimensions, these are 2 dimensions. In 3 dimensions, these are line singularities. Why are they lines? For another mathematical reason. If you have waves of this type are represented by complex scalar functions, and for a complex scalar function to be 0, the real part must vanish, the imaginary part must vanish. Co-dimension 2, points in the plane, curves in space. Well, as I'm speaking in my room, now the sound waves bouncing off the walls of the room and the furniture in the room and so on are threaded by a forest of phase singularity lines. They're threads of silence moving also as broadcast in the room where you are now, moving past your ears too quickly for you not to hear them, because they're zeros, threads of silence. Well, in 3 dimensions, as I've said, they're curves and they can form closed loops. We knew that when John Nye and I understood these phase singularities as general phenomena in wave physics almost 50 years ago now. We realized with examples that we calculated that they can form closed loops. But we wondered, and until 2000s and some decades after, didn't understand whether this could be true, whether the loops could be knotted or linked. Well, they can be, and that's knot theory. And with my then student, Mark Dennis, we calculated that many different types of knots we can make in the zeros of optical fields. For example, knots wound on a torus. So this is a 2-3 knot. You go twice one way and 3 times round the other way, and then join up, and here's 3/7. And we gave to experimentalists a recipe for creating these knots. And so here are some examples of many now. So you take a laser and you make a hologram according to our recipe, which imprints a structure on the light such that downstream and hugely elongated, you get this these knots or links. So here are 2 experimental examples, and this is work by Mark Dennis and Miles Patchett, experimentalists and colleagues. Now, just something rather beautiful about this. If you have been in a laser lab, as many of us have been, you don't see the laser beams if the room is not dusty. You only see the lasers where they hit something. They can be detected. You put something in their path. So here, in this laser beam that you don't see, there's this beautiful structure of zeros that you even more don't see. But of course, if you put a screen at different points, you can reconstruct the knot from its the points of its sections. Very good. These are knotted nothings. They're threads of darkness, threads of black light, you could say. It's now a very large subject. Miles Dennis has continued this far beyond what we did when we started the subject. And it's now a thriving area of also polarization structures can be knotted and linked. Well, I won't discuss that now. Let's discuss extreme interference. For example, when you have many waves in a diffraction grating with n slits. You're all familiar with this, and here's an aspect that you're probably not familiar with. Well, you ask, what's the light at a point P? It's the amplitude, which is the sum of wavelets from each of the slits. And it turns out that what you see depends on a single parameter, call it x. It's the spacing of the slits squared, divided by the wavelength, divided by the distance. Okay. Now, the wave at a point is the sum of all these wavelets. And it turns out that the phase of the nth one is n squared times x. So here you are, the first wave, the second wave, the third, fourth, and so on. And this first phase is x difference, and the next one is 2 squared, the next one is 3 squared. Well, imagine you continue this for an enormous number of slits. Well, it turns out that the resulting mathematics is what's called the Gauss sums of number theory. It turns out that the wave depends sensitively on the arithmetic, on the number theory of the number x. Well, let's have a look at one of these structures, n equals 10,000. I'm calling these things curlicues. Curlicue is a fantastic curl or twist. And I'm choosing a number which is rather small, square root of 101 minus 10. Now, if this number were infinitesimal, you would have a continuous superposition, and these are the amplitude then is given by the Cornu spiral. Well, we don't have zero, we have something very small, and what we have is a spiral of spiral of spiral of spirals going on to infinity with a hierarchical structure. So you start with a spiral, then the sum realizes it's not an integral, it's a sum. It comes out again, another spiral, spiral of spirals, and so on. Now, let's look at a different example, just one more. The golden mean, the most irrational number, and then you get a Christmas tree. So it turns out that these interferences are a kind of arithmetic microscope for the number x. Actually, there's a beautiful theory which Joel Goldberg and I realized worked out in the late 1980s, a kind of renormalization. The curlicue for almost any x contains, if you make n large enough, the curlicues for almost every other x. Very beautiful geometrical structure, which you can explore in detail. It involves fractals as well, as you can guess from these pictures. Good. Something else, more mathematics. Oriental magic mirrors. Now, these are cast and polished bronze mirrors. They're maybe 15 centimeters across, made originally in the Han Dynasty several thousand years ago. Now they're made for tourists. They're not very easy to get hold of, but I have several. They're decent mirrors, and this is my daughter. So they're decent mirrors, but they have an astonishing property. See, on the back of the mirror is a deep cast relief pattern. This particular one is signs of the zodiac. There are various different kinds. Now, if instead of looking in the mirror, here it is, you shine light on it, take it out and into the sun, sunlight shines on it, and you angle the mirror so that you project its reflected light onto a screen, a wall, for example, if you're outside, what do you expect to see? You expect to see a disk of bright light. This is a slightly convex mirror. Well, you do see a disk, but on that disk, and unexpectedly, you see a ghostly image of the pattern on the back of the mirror. Now, that looked like magic, and it probably wasn't deliberately created. It was probably something that people noticed when they made these mirrors and were surprised by. That's why, that's the magicness. Now, because when you look at the surface of the mirror, you don't see anything different. You just see a nice, smooth mirror. Now, it took a while after these mirrors were introduced to the West towards the end of the 19th century to have some idea of what's going on. All kinds of weird and wonderful speculations, wrong ones were raised. For example, the light somehow penetrates the metal. It doesn't. It's a polarization effect. It isn't. But finally, people realized that during casting and cooling and robust polishing, the pattern on the back is weakly reproduced on the front. And I mean weakly, because so weakly that actually, when you look with your naked eyes, you can't see this relief. Now, then, well, that was appreciated, but still it wasn't understood how this pattern that you can't see with your eyes can produce these striking images. And they're not images in the usual sense. If they were, you'd have to focus them. You'd need to put your mirror at a particular distance from the screen. You don't need to. It's stable over a wide range. And it turns out, and this, I understood this a couple of decades ago, 15 years ago, that it's a rather simple but not usually not considered regime of geometrical optics. And it turns out it's another piece of mathematics. That's why I'm telling you that the intensity, well, if it were a perfectly smooth mirror, let's call it 1, but it's 1 plus the Laplacian of the weekly reproduced pattern on the back. There's a piece of mathematics, Laplacian. It's the curvature, the slope of the slope. Now, there's various ways you can test this. One way is here's the observation, but if you take a picture of the back of the mirror yourself and you form this Laplacian to simulate the image, you see it looks quite similar. But there's a much better test. You see, the Laplacian has a property that to every smooth step, it reproduces it as a bright side and a dark side. It's bright on the low side and dark on the high side. So you can test that. Look at this piece of this little region. Here's a step. You can see bright side, dark. If you smooth it up and down, which you can easily do on the computer, you see it very clearly. And in fact, if you then scan across, you can then quantitatively understand the size of these irregularities, a few hundred nanometers, comparable with the wavelength of light, although this is not a wave effect, it's a geometrical effect. And that's why you can't see it, it's too small to see. Just two asides, this Laplacian is used in image processing for edge detection because it enhances edges. Instead of an edge just being a step, it has a bright side and a dark side, so it enhances edges. It's used in image processing, and also in Japan, it's called Makyo imaging. Makyo means wonder mirror. It's used to test the flatness and smoothness of surfaces of semiconductor chips. Now, you want them to be as flat as possible, and instead of what people previously did, which is to go in close with a magnifier or a microscope, you simply need to shine light on and look at the reflection somewhere, and the irregularities show up almost immediately. Now, I wanted to actually detect directly this surface profile, weak reproduction of what's on the back, which I inferred from theory and supported by those observations. So I went to visit Peter Ade. Now, what he does, he tests astronomical mirrors for their surface properties. I mean, you want parabolic mirrors, or you want spherical mirrors, or whatever. So he has laser profilometry. So I took my magic mirror to him and said, can you please scan it? Now, we wanted to see, he can't scan a large area, so we chose this area. And we thought that if we put it through his device, we would immediately see the surface distortions. But we didn't, because this is simply showing you the overall convexity with respect to which this is a tiny invisible perturbation. Now, he has software, and he can subtract off this overall curvature. And when you do that, you still don't see it. And the reason is that although this is a convex mirror, it's not a particularly good convex mirror. It's not uniformly convex. And indeed, if this were an astronomical mirror, this would reveal that the surface is not what you wanted it to be. Now, well, this was very frustrating. And I thought, well, surely this structure must appear. Well, he has clever software, and he had to make a 9th order polynomial fit with using his software, subtracting off one poly after another. Finally, at last, you could see the structure. And when you could see it, you could scan across it. And with this particular structure, it's about a micron. So it's very interesting that this surface profile, this surface deformation of the steps on the back, on the front, which is so easy to see when you just take the mirror out into the sunshine and shine the light mirror on the wall, is actually quite hard to detect directly, but you can. Now this gave us an idea. How interesting it would be to have a transmission version which worked by refraction rather than reflection. These would be Laplacian magic windows. And this is a project with two people in Cardiff and in Hull to create one of these. Now, the idea is the following. You want to find the shape on the glass that would transmit a given image. Well, that involves running the Laplacian backwards, which involves another piece of mathematics, solving Poisson's equation. Now, windows similar to these were recently created independently by two different people, but they're not magic, because when you see them, you can see the surface relief. So they're not Laplacian, but still I'll show you. Visible relief. One is Matthew Brand in MIT, and here's one of his windows. You shine light through and you see this picture on the ground. And here's Mark Pauli in Lausanne. He has this picture of Alan Turing. But again, you can see the irregularities on the mirror. So we want to make these mirrors with surface distortions that you can't see with your eyes. Well, I'll just show you what needs to be done. Here's a simulation. Here's my grandson. He's much older now. My Welsh grandson, Forrest Idris Brynmore Bowen. And so I wanted to see what would be the solution of Poisson's equation with him as the right-hand side. And that would then be the surface profile. Here it is. Of course, this is greatly exaggerated. Here are the contours. Here's the... Just to tell you that when I published this, when I published the theory of the magic windows, I needed from the publisher to get ethical approval from my daughter, from his mother, in order to have permission to reproduce this picture of my grandson in a scientific paper. It's a crazy world. Well, they've made some progress. I won't show you. You see, this is an exercise in what's called nowadays freeform optics. It's a very major area of optical technology, because with computers and accurate profiling, you can reproduce shapes, and that's how those two gentlemen I just showed you, Matt Brand and Mark Pauli, created their plastic. Their shapes, and they very complicated mathematics, computer code, much more complicated than the Laplace equation. But it turns out that to produce the magic windows is a regime of freeform optics that is very difficult, actually. It hasn't been explored properly. And Howard Snelling uses a chemical laser abrasion hybrid method, which is actually quite subtle, and we've reproduced a rather small, only about a few millimeters square, little magic window, just a proof of principle. But to make the big ones that I'm dreaming of is difficult. They're still working on that. This is ongoing research. The final topic I'm going to describe, involving different mathematics, is polarized light in crystals. Now, standard polarization optics, light traveling through a crystal or any anisotropic transparent material oscillates sideways in two possible ways. These are the two polarization modes into which a plane wave will split. So here we are. The light comes in, it's polarized, and these two polarizations, these are the waves that travel undistorted, and the speed with which they travel, that's the refractive index, depend on direction according to matrix algebra. And the matrix describes what the crystal does to the light. The eigenvalues of the matrix are the two refractive indices, the two speeds of the two modes that travel. Well, I want to show you a way where you can see this for yourself, this structure. Because as the waves travel through the crystal, think of a thin slab, the two waves get out of step, and they can be made to interfere by what I'm calling a black light sandwich. Well, what's that? The bread of the sandwich, two slices of bread, are two linear polarizers at right angles. Well, that means that if you had no filling in the sandwich, a poor person's sandwich, it would be black because the light transmitted by the first polarizer would be blocked by the second one. But you do put some filling in, and what you would like is a crystal which is anisotropic in both directions. It's called a biaxial crystal. Now, we theorists don't have easy access to such crystals, but we do have access to a substance that has the same property, and that's the overhead projector transparency foil that decades ago we used to use to project our lectures. And it's interesting, is that substance, we never realized that it has this beautiful property of refracting differently in the three directions. You don't see that when you, in those days, when you projected our lectures, but it has the right properties. And what do? You just, well, you look through it. Well, what's looking? I mean, you have to think what looking is. Looking is directing your gaze in different directions. So you see the light coming through the sandwich in different directions where the two refractive indices depend on direction. And so you see interference fringes, which are constant contours of constant differences of wave speeds. You see patterns like this. Now, these are interference fringes. Good. As I've said, contours of constant difference of wave speeds. These bullseyes are the matrix degeneracies. They're where the two speeds are the same. These directions, we're looking at directions, remember, these are called the optic axes of the crystal. And there are two such axes, and you see here, so there are four such bullseyes, because you have, if you would have light in the opposite directions, you would also see these structures. So these are biaxial crystals. And of course, if you do white light, you see colors, because interference depends on colors, but you see this black stripe. And this black stripe is, whoops, excuse me, this black stripe reflects, is indicative of something called the geometric phase that was mentioned in the kind introduction. It's a general wave phenomena which I won't discuss, but I just will tell you about it, show you now. If you go outside and look at the sky, for example, or any sheet of white paper or wall, you see this lovely pattern if you look in the direction of one of these optic axes. So this black stripe is from a geometric phase, which in this particular example is just pi. Now, if you chose a crystal that was uniaxial, that's a crystal where two of the directions are the same and only one direction is different. Those two bullseyes come together and you would see a black cross. And mineralogists use this to identify, when they look through crystal slabs, the crystals that they find naturally, whether these crystals are uniaxial or biaxial. It tells you something about the crystal symmetry. And since we're talking about mathematics, I have to tell you one more lovely thing. Every point in pictures like this corresponds to a matrix, slightly different from the one I described before. Why? Well, you think of the light coming in that direction into the slab as having two components of the electric field, X and Y. Coming out, it has two components. Well, they're related by a 2x2 matrix. And it turns out that all such matrices, whatever point you choose, whatever direction, whatever substance you put inside, they're all non-trivial square roots of zero. I leave it to you to work out why this is so, but just to tell you the mathematical phenomenon. If I ask you what's the square root of 0, you'll say 0. That's because I will speak of numbers. But if I have a matrix A, B, C, D, there are infinitely many matrices A, B, C, D that when you multiply also by the same matrix A, B, C, D, you get 0, 0, 0, 0. So all of these matrices are, these pictures are contain these, underlying them, these matrices which are non-trivial square roots of 0. Here's another picture. This is taken from the west of Ireland, looking from the village where Stokes was born. Stokes, who taught us about how to quantitatively represent polarization, the Stokes parameters, which tell you about the type of polarization structure that you have. Now, I thought this was the end of the story until I got a very lovely email from 2 Dutch astronomers who'd seen these bullseye structures with the black stripe geometric phase from moving trains in Holland. And you see here, even a reflected one, the train needn't be moving, the train could be on the station. Now, what is happening there? Where is the black light sandwich? Well, the first polarizer is the blue sky. Sunlight, blue sky is sunlight scattered by air molecules, and that produces a polarization effect. The sky is strongly polarized at right angles to the sun. Here's the blue sky. This was understood by Lord Rayleigh. Here he was. When I see this picture, this is how bank managers used to look when I was young. Now, of course, bank managers look like students to me. They don't look like that at all, but this is the impression, very respectable members of society. Well, Lord Rayleigh died in 1919. And in 2019, to mark that event, a number of us were invited to his country home. He belonged to an aristocratic family, which was aristocratic Lord Rayleigh for reasons nothing to do with science. So he was already a member of the aristocracy, and he converted this wing into a laboratory, and we were able to visit this laboratory unchanged for a century. And I was able to hold in my hand his original paper explaining the blue color of the sky and its polarization. Very remarkable. So I wanted myself to see if the British trains produced. I haven't finished describing the explanation. You see, this is the incident polarizer is the sky, right? What about the analog of the crystal slab or the overhead transparency? That's the window of the train, because train windows are stressed, so that if there's an accident and they shatter, they don't shatter into sharp splinters, they shatter into rather blunt angled little cubes. Now, that same stretching produces anisotropy, so those train windows are biaxial. Now, what about the final polarizer? Well, like any good scientist, those astronomers carry polarizers in their pockets whenever they go out, and they just held this in front of their eye, which is the final element of the 3 of the black light sandwich, and then took the photograph. Well, I wanted to do the same thing. So I have also a polarizer that I carry with me, and in British trains, you see the same phenomenon. There they are. Now, what have I told you? And here's another one. A number of mathematical phenomena. Let me list them. 1 + 1 = 2, intensities of light rays. 1 + 1 does not equal 2, intensities of light waves. 2-to-1 map, rainbows. Many-to-1 map, sparkling of the sun on the surface of the sea. mathematical catastrophes, natural focusing, zeros, dark places of undefined phase, knots in black light, Gauss sums in extreme interference, Laplacian, the magic mirrors, matrix degeneracies, polarized light, bullseye. Well, these are just some of the mathematical phenomena in optics. If I chose a different subject, for example, mechanics, there will be, or thermodynamics, there are lots of mathematical phenomena there too. I chose light because it's nice to actually see some of these phenomena. Now, it's often considered, that this connection between mathematics and physics is very surprising. You see, we're astonished to find recently developed and quietly waiting, or sometimes the mathematics developed by physicists themselves, exactly the mathematics required for physics and much more generally than in optics. You know the standard stories. Riemannian geometry awaited general relativity to be revealed as underlying gravity. Matrix theory turned out to be central in understanding quantum states. Now, more recently, fiber bundles awaiting the gauge theories of fundamental physics. Wigner described this as the unreasonable effectiveness of mathematics in the natural sciences. Well, was he right? Is it unreasonable? I actually don't think so. We are beings of finite intelligence. We're recently evolved. We've only been doing science for a few hundred years in a vast, inscrutable universe. Now, we slightly improve our individual intelligences by cooperating and collaborating in science. It's a collective effort. We build as shoulders of giants, as Newton said, but still we're able to comprehend in the universe only those structures that mirror our mental constructs. So at any stage of humanity's development, our most sophisticated constructs are those of our mathematics. So our deepest penetration into the natural world is likely to reflect and be limited by our latest mathematics. And now sometimes the physics come first, some of the mathematics come, that's a detail. So as mathematics developed, more subtle features of the universe become accessible to our understanding. And while our species continues, I see no end to this process, no theory of everything. Of course, it could take a long time between major advances, but I see no reason to think that we're now, with our quantum theory or whatever, at the end of the process. So the unreasonable effectiveness of mathematics in the natural sciences is not unreasonable at all. On the contrary, I think it's inevitable, but it is, of course, wonderful. Now, I want to finish with two quotations. Here is Maxwell as a young man in his 20s, in his private notebook, contemplating what it is to understand something in physics. You need theory. Of course, everything I've described, all this mathematics and optics, you don't just go out into the world and see light and immediately understand catastrophe theory, matrices, many-to-one maps, and so on. He expressed it in this beautiful way. The dimmed outlines of phenomenal things all merge into one another unless we put on the focusing glass of theory and screw it up first to one pitch of definition and then to another, so as to see down into different depths through the great millstone of the world. Very beautiful, in a way, kind of manifesto for theoretical physics. 100 years later, a young man of about the same age made the same point. The point being that we see with our brains as well as our eyes. Modern perception theory sees our eyes as really as an extension of our brains open to the outside world. And that's Paul McCartney. And what did he say? The fool on the hill sees the sun going down, but the eyes in his head see the world spinning round. Thank you.
Thank you. Thank you very much, Professor. So, thank you. It's time for questions, clarifications.
Yeah. Now, can I unshare my screen and see you? I'm not sure quite what to do that. Let me try. I don't know how to. I don't know how to unshare my screen. I don't see anything now.
Yeah.
I don't see any way to unshare my screen. Oh, wait a moment. No, I don't see how to unshare my screen. Just a second.
You please choose stop presenting. Stop presenting.
Yeah. So there are some people raised hands up.
I would be very.
You can go.
But let me just say, first of all, I don't hear very well, so I may ask you to repeat the question to me. And secondly, with this particular connection today, it isn't very loud, and I don't hear you very clearly. So we may have some unfortunate communication difficulty, but still, I'm very happy to try.
Oh. Yeah. Santu, process, you may raise your question.
Santu? Me?
Yeah.
Well, I see something that tells me there are raised hands, but I don't hear anything.
Can you hear?
Okay. Can you hear me now, Professor?
I can hear you a little bit better now, yes.
Okay. I was curious, Professor. The example of Maxwell you gave, that was wonderful. And there's a lot of people who know that Maxwell tried using quaternions before he developed vector calculus for a while, and it was disastrous.
Yes.
And quaternions didn't find a use for another 100 years. So I wonder if there is any scholarly work, or more importantly, if you have any insight into the period of dormancy that a mathematical concept has before it gets fully incorporated into physics. You know,
Well,
because mathematics, you gave the example of Riemann, of course, something like that.
Well, with that specific example, it's actually very interesting because, of course, quaternions were invented by Hamilton. Now, I realized when I tried to read Hamilton that Hamilton's own original papers are almost unreadable. He was a terrible pedagogue. He wrote awfully. People begged him to explain things simply, and he started and he would go off to tangents. But his work was understood and appreciated by Tate, and Tate was the person who tried to make quaternions popular. But Tate was also a student of a college of Lord Kelvin, who was not sympathetic to quaternions, and he never could understand the use of it. Finally, after many years, he said, Tate, I've finally come to understand that quaternions are useful if you want to understand quaternions. So it was unpopular. Now, of course, it came back, and we understand it now, with different Pauli matrices, and people who use image rendering objects. They use quaternions in orbiting ray tracing of objects in three dimensions. Now they are used, not in the form that Hamilton has been using them in quantum minutes without realizing that the Pauli matrices will describe rotations. So must there be a period of dormancy? Not necessarily. I mean, for example, in the gauge theory uses fiber bundles. There was a brief period of dormancy. Once it was understood, and string theorists in particular have been using fiber bundle and developing it themselves in ways that the mathematicians didn't anticipate. So that's one example. An example of in my own world is Divergent Series. Now it was, I mean, divergences were known to Euler, and he understood that they have their uses, but there were many mathematicians were very skeptical of their value, and it was Stokes who, developing Airy's theory of the rainbow, Airy was unable to calculate analytically his integral. He was able to use a numerical method, and we use computers now. But Stokes found analytical understanding of Airy, and he had to understand divergent series. But there was something rather mysterious at the heart of what he did, and that's something which I understood only in 1990. But that's an example of a physicist doing something that the mathematicians didn't do. So although there often is this period of dormancy, I don't think there's a general principle underlying how long it will take to be appreciated, or whether the subsequent developments are done by physicists or mathematicians. But it is interesting. It's the sociology of science. It's a very interesting phenomenon that underlying your question. I won't say more than that.
Right. Thank you, Professor. I was particularly curious about mathematical logic and when it might enter physics, but yeah. And I mean, theoretical computer science, perhaps. But I think there are other questions. Let's stop here.
Okay. Prasad, can you please raise your question now?
Yes.
Hello, sir. I'm audible, sir?
Yes. Speak loudly.
Sir, now is it okay, sir?
Yeah.
Sir, actually in the screen also I wrote down the presence of not like black in light would be static, or it can be vibrating also.
I'm sorry, because of my poor hearing, I didn't catch that. So can you say it again?
So actually, particular question I have written in the in the masses box also. So if it is not audible, you can read maybe.
Professor,
Yes.
can you read the chat box?
Oh, I didn't. Oh,
Yeah.
I don't. Where's the chat box? Let me see that.
The question is in the chat box.
Well, now, where do I find the chat box? Let me see. Just a second.
Downstairs.
Oh yes, it's this thing. Oh yes. Presence of knots. Oh, will be stable. Oh yes. Now. The particular. I didn't say this. Now, thank you for the question. One of the achievements of what we did, you see, something else I didn't say. These phase singularities are also called optical vortices. They're called optical vortices because if you take not the phase but the gradient of phase, this circulates around those lines. So they're examples in light of the much bigger world of vortex structures. Now, these structures, the knots that we were able to produce with knotted vortices, had a property different from all the other vortices, which is that they're static. Because if you use monochromatic light, if you use light that's not monochromatic, then they move. But with the monochromatic light, they're static. So that's how we were able to examine them. They didn't move, they were just sitting there. And if you put the screen at different sections, the knot intersects the screen. I showed you a little example in a series of points, and by synthesizing all these sections, you can create. It's a kind of tomography. You can create. You can understand the knot. So the answer is they're static. But of course, you can. I mean, in light that isn't monochromatic, or waves or sound that are not monochromatic, then the knots are moving. And in particular, and this is something that we also understood, knots can change as topology. Because if they're pieces of string, of course, you can't undo a knot without breaking the string. If it's a closed loop, the strands can't cross each other. But with black light, with zeros, the strands can cross each other, and we understood the anatomy of that crossing. So in addition to our work on knots, we also wrote a paper on knotting and unknotting, where either we change parameters manually or else you have time-dependent waves. So I hope that addresses your question.
Yes, sir. Yes, sir. Till now it was okay, sir. And sir, actually that in the experiment we will have spot, so it could be vibrating, or like it can be static also.
No, well,
Like while tracking the note, so we'll be tracking the note. Like in order to show it, it could be take a geometry kind of loop kind of geometry. So
oh well, because if you can see all the sections, you can easily synthesize them together. I mean, for example, suppose that there was just a single circular loop. Well, if that intersects the screen in pairs of points, and those pairs of points appear and then separate and then come together again as you move the screen, and you immediately infer from that you were looking at a loop.
okay, sir. Okay, sir. Now I got it, sir. It's just a question, sir. The last one, like I was just a bit surprised by the 1 + 1 not equals to 2. So I don't know that is there time in the respective of the intensity of light? Is there time is trivial or what? How like 1 + 1 is not equals to 2? I was not able to understand because because it could be like in the particular time domain we are getting that it's not equal to 2, but the overall the energy should be conserved, right?
Yes, I'm sorry, I didn't really catch that. Please excuse me.
Oh, okay, sir. Okay, sir.
I'm really,
Is it clear now, sir? Is it clear now?
it's a little bit clearer, yes.
Sir, actually, I was just a bit surprised by 1 + 1 not equals to 2. So I was thinking that how the energy should be conserved in the respective of intensity of light. So, like,
Oh,
yes.
you mean with the interference going between
Yes,
0 and 4?
yes, sir. Yes, sir. Yes, of course.
Well, of course, that's actually interesting. I mean, the intensity, if it's light, is the sum of the squares of the E field and the H field, E squared plus H squared. Now, it turns out that they're in antiphase, and so the two interferences cancel each other, and it's constant. Now, it depends on what experiment you do. If you measure E by itself, you can see interference. If you measure H by itself, you see interference. But if you measure E squared plus H squared, and I'm thinking of two plane waves, a simple case, then the interference is gone. It's just a constant. More generally, this is something that Professor Pragya Shukla, who was here in this talk, and I understood, interference is much weaker if you observe E squared plus H squared than if you observe E separately or H separately. Now, I realize this doesn't address your question as I'm speaking now. You'll forgive me for that. I mean, this is just a general phenomenon of interference. I mean, it's the energy when you, okay, if you, in the theory, in standard optics that comes from Maxwell's equations, where you have the continuity, conservation of energy and currents and so on, these are time averages generally. So microscopically, it's rather hard to identify what's happening in any particular situation. You have, okay, sorry, I'm thinking as I'm speaking, not very clearly. You have to consider the interaction of the light with the whatever, however you're measuring it, whatever kind of detector that you have, and then there isn't a problem. I mean, the electric field at a particular point does work on whatever you're detecting, and that's the usual conservation of energy. Just that this phenomenon is different from place to place and from time to time in any interesting wave that isn't just a plane wave. Just go back to the standard textbook arguments about work done by the electric field on any charged object. Or charged object could be a dipole, it could be induced dipole, whatever. But you use the conservation of energy to actually work out the details of what happens, how the energy of the electric field locally is transferred to the detector. I'm sorry it's not very clear, but it takes it's a standard textbook argument.
Okay, sir. Sir, I'm able to understand a bit. Like, is it like for the case 1 + 1 = 2, you have time is not trivial one, but when you say 1 + 1 is not equal to 2 in the perspective of intensity of light, time should
Yes.
be trivial. I think time should be trivial in that case, as I'm understanding.
I missed the second part of that. 1 +
Like,
1
yeah, 1 + 1 is not equals to 2 in the perspective of intensity of light. So I
yes.
think in that case time should be trivial when we are adding the waves of two different amplitude. Maybe it could be, or it could be same also.
Yes, I mean, so 1 + 1 does apply to amplitudes, but it doesn't apply to intensities. So it's another good example of how 1 + 1 = 2 is, although we don't think of it this way, it's really applied mathematics. And like every piece of applied, it may apply or it may not apply. So
Yes,
it's amplitude. And of course, the wonderful thing that
yes,
Thomas Young discovered is that this could be negative as well as positive. So you could get zero. And that, in
yes.
a way, this is the whole essence of wave physics, and it includes quantum physics as well, with superposition of amplitudes rather than intensities. It's a really deep thing that Thomas Young glimpsed all those years ago.
Okay, sir. Actually, I was thinking about the time at that time at the position when we are not getting 2 exactly. So I think there are some more questions. So thank you so much, sir. Thank you so much, sir.
Good.
Yes, sir. Thanks, sir.
So, questions from others? Anirudh,
can I ask
you can raise your,
Yeah.
please.
Really love your talk, Professor Berry. And I have a question regarding your last section regarding Wigner. And you had mentioned that the unreasonable part in the Wigner's article, that unreasonable effectiveness of mathematics,
Yes,
that
indeed.
it's not unreasonable. It is pretty understandable, and it is inevitable that we would see these mathematical applications make sense in a physical world. But I would like to argue that in a sense, Wigner was right in calling it unreasonable, because what is being said here is maths, basically when used in the physical world, is nothing but just manipulations. And that's the main reason why physicists chose to use or would use mathematical explanations for their physical models. And on top of it, he himself also mentions that for several examples, including Hilbert space, or whether it's gravity and so on, that it is unreasonable, because even though we do manipulate you use mathematics for trying to come up with a proper explanation for the model, we are almost always right. And in fact, even in your own example, when you mentioned the use of Laplacian and Poisson's equation for magic mirrors and magic windows, it's basically you're manipulating your own idea of Laplacian into a Poisson's operation form to explain another physical phenomena. So basically it should be unreasonable, because we are not supposed to play around with things like that and be right almost all of the time.
I missed the last sentence. Say it again.
Okay. So regarding your use of Laplacian and Poisson's equations for the magic mirror and magic windows, if you use Wigner's idea that maths is nothing but using, manipulating using maths and physics is nothing but manipulating mathematical ideas to fit the physical description, you did do just that by using, mathematical ideas to have the Laplacian Poisson's equation, changed it up a bit so that you could explain these two different phenomena. So And by doing such manipulations, you don't expect yourself to be right most of the time, but you were. And so that's what makes it pretty unreasonable that, according to Wigner, that we are right most of the time. We are right most of the time, even though we should not be.
Well, I would respond differently to that, because you're assuming that no theoretical physicist has a waste paper basket. Mostly we're wrong. I mean, when I'm writing a paper, I describe what I did that worked successfully, and not all the attempts that I made which failed and did not work. So when you say mathematics works almost all the time, it doesn't actually. I mean, when you're doing science, it's a kind of Darwinian process. I mean, what you read and what we publish are the mathematical explanations that survive, and not all the ones that don't survive. But I see this as a side issue. I mean, there is something that I agree with in what you said, which I didn't emphasize. It's a rather different subject, which is that our explanations are, in fact, Niels Bohr made the point with respect to quantum mechanics. It applies more generally. Science, mathematics, is not just about the world, it's about our interaction with the world. I mean, we decide at what level we want to examine something, and it's very slippery if you ask the question, what is really there that we're explaining, because it's a choice I mean, I give an example. If I ask the question, many of us are wearing glasses. I'm wearing glasses now. If I ask the question, how do those glasses work? Well, the simplest level, we say, well, you look at the light rays and they're focused and they get an image on the retina, and depending on the curvatures, it all works out correctly. And this, we think, is the explanation. But then we think, well, look, we know that light rays don't actually exist. They're approximate concepts and approximation to waves. And so if you then take your glasses and you want to understand what's happening using waves, it's much more difficult, but then you get more information, the detailed structure, nearer focus, and so on. Then you think, well, these waves are really electromagnetic fields. So you actually have polarization structures. Well, you can study those. They're being studied actually now. It's contemporary work. And then finally you think, well, but those electromagnetic, well, really, you have quantum fields. These electromagnetic fields describe the probability of detecting random events if you put detectors there. So then you say, well, okay, you've got 4 different levels of explanation of how your glass works. Which is the real one? The answer is all of them, none of them. Now, physicists might think, well, okay, you take the deepest level, the quantum, but that would make reality history dependent, depending on whatever our latest theory is. If your theories change because you discover something deeper, then reality will change, which seems unreasonable. And moreover, the deeper you go, the more remote you get from the phenomenon you want to explain. Try understanding how your glasses work, starting from quantum electrodynamics. You never would do it. I mean, it's the wrong level. So there is a large element of our interaction with the world. I'm not denying the world, of course, but we pay attention to bits of it, and we model it in certain ways, and we call that reality. But it's actually quite a subtle thing. So you alluded to this when you said that there's some element of choice in our application of mathematics, and that's what I've just described. I've written about this. If you look on my homepage in Physics World in 2020, I have this. I use this Buddhist phrase: true but not real, real but not true, and in disentangling those notions of what we, how we can perceive those bits of the world which we choose to understand, and then of course with the mathematics we may or may not be successful. So, I'm just speaking with ideas which are evoked by your comment. So I don't, and by the way, I'm not disparaging. It's a very beautiful paper, what he wrote, this unreasonable effectiveness. It's just that I wanted to argue why there's a sense in which it isn't unreasonable. It's inevitable.
Okay, Professor. There is one more comment or question in the chat box.
Oh, yes.
Yeah.
And it's 1 + 1. We should be maybe we polarize a particular time domain. 1 + 1. Yeah. Time is not. Oh, I agree with that. I mean, I completely agree. Yeah, of course, time. If you, yeah, exactly. I mean, this phase difference, which is responsible for anything between 0 and 4, is of course time dependent. So it's also space dependent, but it occurs in time as well. So yes, I agree with you.
Okay.
Yeah.
So any other question? Professor Pragya, do you have some questions?
Thanks. No.
Okay. So